Hello, so we are doing the basic power flow equations, and we are learning how to derive them so that whenever we are in question of how we're going to solve a power flow problem, we can just derive the equations from basic Ohm's law. And this here is then a 3-bus system, and we know that when there are 3 buses we have some impedances, and we can make that into admittance matrix. So if you're wondering how to do that, look at the previous video. We know that this is admittance matrix here, and we know that at these points we have P and Q bus. Here there's a P V bus, and then this is the slack or swing bus, which is also sometimes referred to as the actual reference bus. So let's get into the job, and this is first done from Ohm's law. We're just going to state that one, so just starting from that, right, the basic Ohm's law. So that's V is equal to resistance times current, so that's how we find the voltage. And then we know that this voltage is a complex number, so it means that it has some magnitude and then it has some angle. So this is the load angle delta. And then we know that that voltage is then also in Ohm's law. It's affected by the impedance, and then we have some complex value for the current as well. It will be leading and lagging according to the value of the impedance. And then we know something else here, is that we can apply this principle or this law of duality, which then again is stating that when we have impedance, we have also its inverse, which is the admittance, and that's how we derive this admittance matrix. So that's 1 over set, or 1 over the impedance. So that means that I can look at this from the perspective of the current, because that's the duality principle that we apply here. So it means that this complex current is nothing but the complex admittance times the complex voltage. So that means that these admittances have some connectivity, and it also has some susceptances, right? So that's the G and the JB notation there for your admittance matrix. So now I'm just going to take the matrix notation and just drop this complex bar, because it's sort of given that this all is in complex form. So then I have Y times V, right? So this is then obviously n times 1, and this is some n times n according to the number of buses that you have, and then again n times I. So let's get back to these further derivation, and if we go in here and we look at this row 3, so we call this row 3 some k row, so this is the kth row that we're looking at. And so if we are at kth row, so let's say that that's for this case, because if we're looking at this row 3, we are going to get the current that's injected into this bus here, 3. So that means that we have IK is equal to Y31, and I have to multiply that by the V1, plus Y32 times V2, plus Y33 times V3. That's Y33 times V3. So this is all some expression of that kth row. So I can then so actually what I was doing here was not the kth row, because this was actually the 3rd row, yeah, looking at I3. So if I want to generalize it, I can say that because eventually I want to look at the second row and the first row and looking at it all together. So that means that if I have ik, I hope I can just generalize and say that this is the sum of I from 1 to n yk I times vi. And then we're going to use some information from this bus system, because we know something here about some voltages, but we also know something about this P and Q. So that means that what we can utilize is this complex power, which is nothing but V times I conjugate. And V times I conjugate, we can just rearrange this and look at the current itself. So and that's the current injected here, right? At this bus 3 or whatever bus you're looking at. And that's going to be S conjugate over V conjugate. And that means, again, like if we're looking at IK and we have this expression, it means that this is then equal to this power that we have at this kth bus. So I can use this relation here to find out something more. So let's say that this is ASK conjugate over VK conjugate. Right? So far, so good. So, what we are looking at then is that if I just write out this expression, because I'm going to do this for a number of buses. So not only for 3 bus system, but for 5 and 10 and 25 and so forth. So what you're looking at then is that you have an expression here, which is, you know, IK1 times V1 plus YK2 times V2 plus blah 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 all the way up to YKK times VK, and then even further up to YKN times VN, which then is equal to SK conjugate over VK conjugate. And then we wanted to look at one particular bus. So we want to look at just like we looked at the kth row, we want to look at this K bus. So let's just have a look at that. So that's this one here. And we want to separate out this one. So it means that I'm now just going to make some space and then put this on the left hand side. So that's YKK times VK is equal to this SK conjugate over the VK conjugate. But then I have to take minus this expression. So that's going to be the sum of I equals to 1 to n. But here I cannot be k because that's already in this expression. So this is minus YKI times VI. Right? And then I want to look at VK alone, and I want to solve for this complexity again, because I know, this is another thing that I know, is that this SK conjugate, or let's just take, for now, just take S at any S, is equal to P plus JQ, because that's going to help us in noticing that when we go for VK here alone, I have to take this 1 over YKK. Then I have to take this SK conjugate. And then the conjugate here, if this is P plus JQ, I have to take PK minus JQK over the VK conjugate, which stems from here, VK conjugate, and then minus this term here, which is then the sum of I equal to 1 to n but I cannot be k, so that's yki times vi, like that. So this one here is then useful for our first method, which is then Gauss-Seidel. So we're going to go into the numeric expression of that in a while. Then I'm just going to copy this one, because this is useful, this expression here, to get another view of this. So let's copy this, take it down here, because you see, everything of this derives from the same place. So when I have this one, I just need to get back to here, make some space. I want to look at SK conjugate. So what I'm going to do here is I'm going to multiply by VK conjugate. So this was also K, right? And what I'm going to do then is that I'm going to get this expression here, SK conjugate here, is equal to PK minus JQK, just as before. So then this conjugate is solved, right? And then it's the sum of I equals to 1 to n of yki times vi times vk conjugate. So the next question is, I have to solve for this conjugate. And the way to do that is to apply polar form. So I can simply state here that pk minus jqk is equal to the sum of all of this, from 1 to n, of the magnitude of yki times vi times vk, and then I solve the conjugate with taking the angle to all of this. So that's minus delta k plus theta ki plus delta I. So that's the theta that goes with all of these impedances and their angles, right? So that's theta ki. And for Newton-Raphson, I want two equations. So I'll look at the active power, pk. So that's going to be the cosine. So that's nothing but the sum of I equals to 1 to n of, just to clean up a little bit, I take vk first, times yki times vi, and then I have the cosine of delta I minus delta k plus theta ki. Right? And then for the qk, this is going to be minus, so I'll take the minus from here, and then j is going to go with the sign, so just look at this, it's going to go from I equals to 1 to n, magnitude of vk times yki times vi, and then the j that was here went out with a j here, and then we're at sine delta I minus delta k plus theta ki. So these two equations then will be these two here, and they're going to be useful for Newton-Raphson method. So then we have the both lined up here, Gauss-Seidel and Newton-Raphson method. So that's the derivation of, or how to derive the load flow equations.